Hello and welcome to another Solana tutorial. This is another episode of the Solana development course. Because James has published some new lessons. In fact, he published an entire new module, Module 8, Advanced Solana Programming. So today we'll talk about program architecture. Why not? Let's do that. Then he also has a cryptography fundamentals now. Yeah, symmetric and asymmetric cryptography. The basics. It's very basic. You can go through that if you want. But yeah, that's great that he has that now. And those lessons we already went through, they're green. Yay! And I got really good feedback on them, that it was really helpful for people. So in case you haven't seen those videos, there's a playlist. You can go check that out. Because those are really like the basics of Solana development. And now we get to advanced Solana programming, and we talk about program architecture. This is great because I can also learn something here. And essentially that's why I'm doing this. I'm learning with you. I might be a bit ahead, but still we're learning together. Our objectives are to use box and zero copy to work with large data. Oh, that's actually interesting. Yeah, I want to do that. Make better PDA design decisions. Oh, that could be interesting. I don't think you can teach me much there, and I do think we have talked about that in other videos, but it's good that the course goes over that as well. So yeah, definitely interesting. Future-proof your programs. Don't know what that means. Could mean like a lot of things, but I'm interested in what James has in store for us. And then we deal with concurrency issues. Solana can process in parallel, but you can still run into bottlenecks. Ah, okay, that's what they mean with concurrency issues, right? So if we have shared accounts that all of the transactions need to write to, that can lead to problems, yes. All right, nice. So yeah, program architecture, an important topic if you develop more than a simple counter program or something. If you start to develop more complex programs, you want to think about that. Because so far, all we did was like this note-taking app or simple stuff. But when we actually want to build something bigger, then we need to think about all those design choices. So that is program architecture. We need to be the architect of our program. So this is going to be a fun episode because I did see this box thing before. Basically, we can't put all of the data onto the stack, so let's put it in the heap. That's what the box does, but that's all I know about it, and I've never actually actively used it. I've just seen it in source code, so that should be interesting. And then the zero copy apparently is for accounts that are even too large for the box, so too large for putting it on the heap, then we can just have a zero copy. The size and order fields, put variable length fields at the end. Okay, yeah, that is something that I have been mentioning before, even in this course. Obviously, if there are fixed length things, we want them in the very beginning because then we can work with fixed offsets. And as soon as we have some variable stuff like a string that can have arbitrary length, yes, we can put it in the account, but from that point on, we can't go with fixed indexing in there anymore. We need to read the length of the string and then jump there and then read that length, jump there, read that length, jump there until we get to the thing that we actually want to have. And for that, we need to have all of those parts in memory, which for big accounts, you want to only have parts of the account in memory. I think that's what this zero copy thing is. And therefore, how you structure your accounts actually matters. But okay, let's really get started here and check out what James is talking about. So, program architecture is what separates the hobbyist from the professional. And we totally want to be professional Solana developers, don't we? We don't want to be no script kiddies. We want to be professional smart contract developers. Yeah. Crafting performant programs has more to do with system design than it does with the code. And you as a designer, the architect, need to think about what your code needs to do. So that's the simple stuff like, what's my program actually supposed to do? Like the functionality, functional requirements. And then what possible implementations there are. So how can I make my program do the thing that I want it to do? And then what are the different trade-offs between those? right? Because we can do stuff in different ways, and we need to know what are the advantages and disadvantages such that we pick the one that is most suitable for our thing, which again depends on what the code needs to do. There is no one solution for everything, right? There is no perfect sorting algorithm. There is no best data structure. It all depends on the use case. What do you need the data structure for? I'll give you an example. Because we were just talking about this, that you need to put the variable length fields at the end. When storing strings, we can either store the exact length of the string, like 4 bytes for the length, and then the string, so the data of the string, or we allocate a fixed block such that every string needs exactly that amount of data. And then we just write our string in there and keep the rest 0. So it will always have this size. So those are two possible implementations for strings, and they both have advantages and disadvantages. The advantage of the fixed size version is it's always the same size, so I can always start reading the next thing right where the string ends, and I know where the string ends without first having to read how long the string is. The disadvantage obviously might be that I'm wasting storage. All those 0 bytes at the end, I don't really need them. If I have something like a symbol where I know that it's between like 3 and 5 characters every time, then making it fixed is pretty helpful. Whereas if I have random text that can be like several hundred characters long or just a few characters, then doing the variable with the length in the beginning actually makes much more sense. So knowing the trade-offs for the different implementations and then choosing the one that makes most sense for your program, for your use case. This is program architecture. Because both of the strategies work, just one is more efficient for your specific use case. And we want to have our programs as efficient as possible because we're professionals and not freaking hobbyists, right? And the whole thing with the scaling and whatever. I'm talking a lot, interpreting what James writes, but that's okay. That's what I'm here for. Making all the text easily digestible. Text. Blah, 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 blah. It's even more important when developing on a blockchain, because not only are the resources more limited, but we're also dealing with people's assets. Code has a cost now. Yes, code literally has a cost. And we were talking about that in our security lessons. But there are specific limitations to Solana development that we don't have in other programming environments. For instance, how much data can be stored in an account? That is limited because those resources are limited. In your server, you can just throw in more RAM and bam, you're fine. On Solana, that's not possible. We have those strict constraints and we need to stick to them. And that's why finding a good solution for those things is so important. Because if we're not efficient with what we do, then yes, it might work for small things, for small programs. But as soon as we deal with like a lot of data or a lot of users and therefore a lot of accounts or bigger accounts, then we might hit those limitations of Solana and we can't go further. That's what happened with the token metadata program from Metaplex. At some point, it just got so big that it can't go any bigger because Solana constraints. That's why they can't add any more features because the program is just too big already. So we need to be efficient and we need to structure it well and maybe also do one program per use case and not one monolithic giant thing that does it all. But let's not judge the architecture of that program too much. So yeah, how much data we can store is a limitation. The cost to store that data, especially on-chain data, cannot be ignored because that costs actual SOL and somebody gotta pay that. And if you have a 10 megabyte account, then you suddenly pay 69 SOL. You gotta think twice if you actually wanna spend that much money on an account that you might not even need or might be able to have it much smaller. And then another limitation is also the compute units available. We've talked about that. So yeah, there are constraints on memory and there are constraints on compute, the two things that make up computer programs. We did talk about that in another video on compute units. So yeah, those are the main constraints. And now you as the program designer have to be mindful of those limitations. so that we can make programs that are affordable, fast, safe, and functional. So they actually do what they're supposed to do, can't be easily hacked, are responsive, good UX, and we can actually afford to deploy it. Today we'll be delving into some of the more advanced considerations that should be taken when creating Solana programs. Yeah, James, let's do it. Good. So, this looks like a huge module though. Wow, really interesting topics today. Step 1. Dealing with large accounts. James once again says that in normal computer programs, we don't really have to deal with those limitations so much. We can just be like, yeah, 4,000 character limit for a string is fine. Storage is cheap. And every integer, we can just make it a 32-bit. So it's always an int. That's fine. And for most normal computer programs, unless you're working on a resource constrained environment like embedded systems or high performance computing, where it could be an issue, like even on my Raspberry Pi, I wouldn't worry too much about those amounts of memory. However, on Solana, I have to. Well, have to. I can be like, I spent all that sol. But yeah, we want to be efficient. Because on Solana, we have limits on the heap, stack, and on the account size. So account size limited to 10 megabytes, and that's a super expensive account. Don't know the actual limits for that. Maybe I'll learn it here. But yeah, there's only so much we can put in those memory. Oh, by the way, in case stack and heap are terminology that you have never heard before because you didn't study computer science like some other people did. How can I make this really, really short? I'm going to give you a very, very, very high level overview of this. And if you're interested, go read it up. Like heap and stack, you'll find information if you just Google that. They're both data structures and they're also parts of the memory of a computer program because they correspond to that data structure. That's why they have the same names. That's a bit confusing sometimes. But anyway, in this case, we're talking about a program's stack memory, which is basically small memory where all this stuff is just put on top of each other. So we call a function, all the function parameters live on the stack then, the stack frame, and then another function, and we put that on top. And if we return from the function, we jump back in the stack. And because that's all sequential, there's only so much that we can put in there. The heap, on the other hand, is more of a free memory where we can request some memory and then we have some bunch of storage available and we can fill it as we see fit. And there's no order. We can request several of those memory blocks. So in general, we can fit more memory onto the heap than we can fit on the stack. And if you want more details, just read up on heap and stack. Oh yeah, and per default, all our variables and stuff lands on the stack. If we don't specifically request memory from the heap, then everything per default is on the stack. Okay, that's the basics, because I recognize that those words are just thrown in here and you might not know what it is. Those are places in memory, different kinds of memory. Okay, right. And because of those limitations, we need to be more careful with where we put our bytes. Okay, and we have the following concerns. Since we pay per byte, we want to keep our footprint small. Yeah, because we want to pay less, because we're cheap, because that's actual money that we pay for this. And the other concern is, when operating on larger data, we run into stack and heap constraints because they are also limited in size. So that's the size that the validator can provide for executing. Because if executing your instruction needs too much memory on the validator, then at some point the validator will not have enough working memory to support all of that, and therefore it would go down. That's why we put constraints on that, such that every execution can only have a certain amount of memory, because then the validator can be sure, okay, if I limit it to that, then I can support this amount of transactions. So, because also the validator needs to keep themselves safe from an attack where an instruction would just fill up their memory. Yeah. And so to get around those constraints, we'll have a look at box and zero copies. Okay, good. So let's talk about sizes. How old am I, 13? Let's compare sizes. In Solana, a transaction's fee payer pays for each byte stored on chain. Technically, I wouldn't say it's the fee payer. The fee payer, per my definition, is the guy who pays the transaction fee. But that can be a different guy than the one who pays for rent. Don't really agree with that sentence, but there's always somebody who pays for the bytes stored on chain. And that's what we call rent. You can have a intro to rent. And I think by now we're far enough that we don't need to go through. Sorry for changing black to white, but there's no dark mode here, sorry. Blah, 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 blah. Rent doesn't actually really exist anymore. It's more a deposit. Yeah. And everything needs to be rent exempt. I think we went through this enough times. But the point is that putting data on the blockchain is expensive. That's also why the NFTs store the attributes and the image stuff off-chain, because putting all of that on-chain would be super expensive. So we want to find a balance. When I read that, I think trade-off between the program being highly functional and expensive, right? If I want my program to be able to access all the data, I put all of it on-chain, but that's more expensive. So it's always a freaking trade-off. And we want to find the balance. Right. And so that we can start optimizing for storage space, we need to know how big our data actually is. And we have looked at this in the Anchor book in previous episodes. Here it is again. So you see a U8 needs 1 byte, a U16, 2 bytes, and so on and so on and so on. That's pretty intuitive. A pub key is always 32 bytes. An array is the length of the array times the space for one element in the array. Then the vector uses 4 bytes to indicate the length of the vector, and then it's that many times the space that one element requires. String, similar, also 4 bytes for the length, and then the actual bytes of the string, so the characters. And optional takes the first byte to indicate if that option is set or not, and then if it's not set, then nothing else, so just this 1 byte. And if it is set, then the amount of space that this element needs. An enum, and this is also interesting, is that I have not in my active memory, is 1 plus, so 1 byte, and then the largest variant of the size, because an enum can have like those inner values or whatever you call them, I don't know. Or variant, that's what it's called at the enum. And depending on how big those are, because those can be more complex things. In this case, we have a U8 and a U16. So the largest of those is the U16. So the total size of the enum will be 3 bytes, because 1 plus the 2 from the U16. Floating point numbers, also pretty self-explanatory. Accounts need 8 bytes plus the space of the account. Why? Because the anchor adds this 8-byte discriminator to each of the accounts, which is not part of this struct T. And regular data struct just needs the space that the struct requires. That's also pretty intuitive. So yeah, pretty clear, all of them. The one thing that I do want to point out here, because we might bump into that later again, is that a Boolean also requires 1 byte. And the Boolean can only be 1 or 0. So essentially, we'll always just use the 1 bit. So theoretically, we would just need 1 bit, but we don't want to work with offsets that are not multiples of bytes. That's why a Boolean will always also require 1 byte. Which also means if you have several Booleans, you could optimize that into a U8, for instance, because there you could have 8 Booleans essentially stored in 1 byte. You just need to work a bit with bit operations to get the individual values out. But yeah, if you want to be efficient, you can use U8s instead of bools, and maybe we'll read more on that. Or is there more on that to read right now? Let's go through that, because we already started talking about it. There, data optimization. Instead of making an account struct like this with 8 Booleans that requires 8 bytes, we could make one with flags, but that is just a U8, and that just costs us 1 byte. And each flag is 1 bit. So that's the first bit, the second bit, the third bit of this U8, of this byte. And all of them 0 would be this. And then we could use all of those in combination just by using a binary OR and a binary AND to read if it's the case. But yeah, that's just some programming basics. You should be able to figure that out, or not. If not, then maybe at some point we talk about it. Let's get back to the storage sizes. So knowing these, we can start thinking about our optimizations. For example, If we have an integer that will only ever reach 100, like for instance, you want to store some percentage with only exact percentage values, then we don't need a U64 or even a U32. We only need a U8, because with a U8 we can store 255 values, and we just want from 1 to 100. Or if it's the level and your maximum level is 100, right? You can store the level in a byte. You don't need a bigger integer. And then James says, be careful though, you can quickly run into behavior due to overflow. So obviously if you accidentally use a too small value and then you go over it, then you can run into some issues of stuff not working, or your program being exploitable, or just always failing. If you use anchor, then automatically at over and underflows it will throw an error. Cool. Now let's finally get to the interesting part. Box. Now that we know a little bit about data sizes, we can skip forward and look at the problem you'll run into if you want to deal with larger data accounts. Let's say we have the following thing. And I guess I'm gonna get out my... because you only really learn by doing, not by reading about it. We have some big data struct with 5,000 bytes. 5,000 bytes. And let's say we wanted to access this big data struct. We just provide this as our instruction accounts with this context. Oh no, you're installing everything again? That's why I can't be a productive Solana developer, because just every time. Okay, never mind. Not important enough. We are just gonna go through it like this then, because I cannot be bothered that every time I need to fix the same issue, which let's see how easy it is to get that to work. Nice. Okay, try that again, please. All right. I mean, I've just spent an hour so far to get that set up. I got time, and through the magic of video editing, you got time too. So basically, what we are totally going to see, or what we saw through editing magic, is that we get this error. So basically, the problem if we do something like that is we will put all of that on the stack. So we have 5,000 bytes for this thing alone, and per default, we'll put it all on the stack. Every stack frame on Solana apparently is only 4 kilobytes. So that means we can only put 4,000 bytes on the stack in every function. So for simplicity, let's say in every instruction, we only have 4 kilobytes of available stack storage, stack memory. Which means that if we have such a big thing, that's just not gonna fit on the stack. And if we try to compile it, so this is already a compiler warning, even at compile time, we can make sure that we can put everything on the stack. So we can check that beforehand, not at the execution, but when we compile it, we can see, oh, our stack frame is too small for the amount of data that we want to put on the stack. Therefore, this is not allowed. We can just not do this. We cannot put all of that data on the stack. So the stack is the static memory allocation for those local variables. So always 4 kilobytes per stack frame. So we never have more than this. Why do we always have 4 kilobytes again? Well, such that we don't need to remember how big it is, but we just always have 4 kilobyte blocks. Then it's clear in the memory 4 kilobytes, 4 kilobytes, 4 kilobytes, and then when we're done with the stack frame, we just drop 4 kilobytes. So how do we fix this? The answer is the box. So we just box this entire account. So we put this box thing with a generic of whatever we had before, which means that you put all of that into the heap or onto the heap. I don't know, wherever. You put it in heap memory. So box means put it in the heap. Should I make a song about that? No, not now. Box it in the heap. There is a song there, and I'm not gonna sing it today. The box, in Anchor, that is, the box is used to allocate the account to the heap, not the stack. Which is great, since the heap gives us 32 kilobytes to work. So 32 kilobytes, which is, 8 times as much. And yeah, Anchor conveniently deals with everything. We don't have to do anything. We can just add this box, and other than that, it's completely the same. We can still work with all the variables in there as we would And Anchor knows where to read them, write them, and then persist them back to. Anchor abstracts all of this away. All we need to do is add this box, and then it's automatically put in the heap. And that's all we need to do as a developer. Which, of course, can also be exploited. You don't want to just put everything in a box just so you're sure that there's enough space. No, you just want to put those things in a box that can't fit on the stack, and where it makes sense that you want the entire thing on the heap. So you need to think about which ones you box and which ones you don't. As with here, also with the data, you want to think about what data you need and not just be like, yeah, we just put a string of 5,000 characters because we can, and then we just put it in a box because it works anyway, right? It's not the strategy that I would recommend. It's a strategy that works up until some point where you reach the next limit. But yeah, it's not clean. It's not good program architecture. And that's what we're learning here today. You can still overflow the stack with sufficiently large accounts. But first let's stay here. And now, the moment we've all been waiting for over an hour. Yes! If you're that happy with it, building. Okay, so I downloaded the thing that James provided, which actually built out of the box, which is good. It just took a while. So we have a big data account. This big data account we put in a box. So if we were not using this box, let's remove that. We should already at compile time get an error here. In 3, 2, 1, error. Yeah. See, stack offset exceeds maximum offset of 4096. So 4096, those are the 4 kilobytes, because again, a kilobyte is 1024 bytes, but yeah, about 4000. And we're off by 500 bytes. Please minimize large stack variables. That's what the compiler already tells me. So it tells me which function, a bit weirdly encoded, but yeah, but we see where it's from in this program, in this folder, this file, this struct, and then where exactly. So that's the error. Even with 2000 U8s, let's say if I had 5000 here, and I would be off by even more, offset of 5000 something. Weirdly, if I'm back to 2000, there are more. So here it exceeds, and then here it exceeds again. First time with the 5000, and then with 10,000. And if I add the box again, I still get an error that will exceed, but with 2000 we did not get that error. So apparently what's written here in the comments basically says it's not really in the heap as it would be with regular Rust, but this box just references the original storage, like the on-chain storage. Since Solana validators need to have all the state in memory anyway, they reference that directly, apparently. Something like that. So the box is not actually a reference to the heap, but really to the on-chain data directly. Which doesn't explain to me why I can't have 5K here. Whatever. With 2000, if we put it in a box, then we can compile it. But then, if we use something even bigger, if we have 1000 times U128, what is that? 16 bytes. So that's 16,000 something bytes. That's some really big data. For Solana standards, we must say. For Solana accounts, this is huge. I mean, that will cost you... Oh, I would have expected more. Hold on. Yeah, it's still just 16 kilobytes. I was thinking in megabytes. Okay, never mind. It's just a big account then. I mean, it's still affordable. It's just cost 0.1 sol, right? Okay, we can pay. But I mean, €2 for an account. We don't want to have too many of that. Anyway, we can use that, but then we can't get it all into the storage anymore. If we were to use a normal account with this, some real big data struct, then we get a bunch of stack offset, exceeded max offset again, exceeded max offset by 29,000 bytes. So yeah, this is already giving us errors and it won't work if we started it. So let's discuss this zero copy thing. Sorry for flashing the white. Let's discuss this first. With the box, we can deal with a medium-sized account. But what if you need really, really big ones, like 10 megabytes? We can't have all of that in the heap. So in this example now, with the really big data, with the 16 kilobytes, this will make the program fail even if we had a box. So even if we were boxing that, we still get the offset of 16K exceeded our max offset by that many bytes. Please minimize large stack variable. So apparently still with boxes, it puts stuff on the stack. Okay, so what can we do if we really want this really big data account? It has some data in there that we want to read. What can we do? We can use this zero copy. And zero copy, contrary to what I thought when I first read this, that it copies it with zeros, I think what that really means is it does zero copying. So there is no copying, zero copy with this account. So it doesn't copy any data from the actual account to working memory. No copying, zero copy. I think that's where that comes from. So basically, we add zero copy to our account struct like this. Let's do that. So our really big thingy gets a zero copy. And then we add zero as a constraint to the account validation struct, so it doesn't perform those checks apparently, right? Because if I have the zero here, copy this and say zero, then I get one error less here. So apparently it doesn't do that check then, such that we can load that. And then we need to wrap the account type in an account loader. So first of all, remove the box, that was useless. And instead of account, we say account loader. So it doesn't take the entire account, but it takes a loader object. So it will lazily load the data later. And with that, it should then compile again. So we have zero copy here, zero here, account loader here. That should now give us our really big data account. Yep, that builds. So to understand what's happening here, take a look at the Rust Anchor documentation. Other than being more efficient, so this zero copy is more efficient, the most resilient benefit of zero copy is the ability to define account types larger than the max stack or heap size. Import the account has to be copied, and this, can I read it here? Zero copy deserialization is an experimental feature. Use only when necessary. Ability to define account types larger than the max stack or heap size. When using Borsch, the account has to be copied and deserialized into the new data structure, and thus is constrained by stack and heap limits imposed by the BPF VM. So the VM limits stack and heap. But with zero copy deserialization, all bytes from the accounts are simply reinterpreted as a reference to the data structure. So it's all just a reference to the original, and no allocation or copy is necessary. So since there's no allocations or copies, we can just get around this limitation because we don't add any more data. We don't need to store something in the program. We don't need to temporarily have memory available for that because it's all just a reinterpretation of the existing memory. To facilitate this, all fields of an account must be considered to be plain old data, so they must implement the pod. Using zero copy requires bytmuck with features derive and min-cos generic. So maybe also interesting, you need to have that added here, bytmuck in the cargo toml. Otherwise that won't work with a zero copy. Okay, so basically our program never actually loads zero copy account data. It just gets a pointer to the raw data, whatever that raw data is. Because the validators need to have all the state of Solana to do the checks anyway, so the accounts that I'm using in my transaction, the validator needs to know the data for that. So it's somewhere in memory, and we just point there, wherever that is. That account loader ensures this doesn't change too much about how you interact with the account from your code. So that's apparently an abstraction, I think, that we can more easily use that pointer to do stuff with it. so that we can actually reference that data and not have to work on the byte for byte for the actual full account. There are a couple of caveats though. First, we cannot init. This is due to there being a CPI limit on accounts bigger than 10 kilobytes. So this won't work. Instead, your client has to create large accounts and pay for its rent in a separate instruction. So it needs to go through the system program directly, a create account where we say how much space we want to allocate and do that in a separate instruction. But not a separate transaction. It can happen in the same transaction because it's just on the CPI that we have this 10 kilobyte limit. If we do it directly without CPI, then it's fine. Second caveat, caveat. Anyway, second caveat is that you'll have to call one of the following methods inside your Rust instruction function to load the account. So load init and first initializing an account. Because Anchor expects that account to have the discriminator already. So load init ignores that the discriminator is not there. Load when we just normally load an account, and load mutable when we want to load that account and write to it as well. For example, for our really big data struct, we could do the following. We use this load init, context accounts, some really big data. We load init, then we have the really big data account, and then we can work with that like it's a normal account. Oh, there's a video. Jonas did a video. Now you have my video as well. Yeah, so essentially, coming back here, what we need to do is load that with load init, which will then give us, hey, Rust analyzer, why don't I have types? But anyway, it's probably like an account info. We can then access the really big data, which is this. We can read the length from it, and we could even write some data. Because again, one index here is a U128. So this is big numbers. So this thing is also just one U128. And I write to the last index. Note that load init obviously loads it mutable. So what load init really does is it does a load mute, and then it writes in the first 8 bytes the account discriminator, because that's what Anchor needs. And then once you just load, then it will check the account discriminator. And if you load mute, it will also check the account discriminator and then let you modify the data. That's why here we can modify the data, because load init will load it as mutable. Yeah, so far so simple. The only difference is that we can't say some really big data dot really big data directly. We first need to go through this load init, and that could fail. That's why here we get a result. So that's why we have here the question mark. If that fails, then we just return an error. But if it doesn't, then we can use this big data and access it as we usually would. Yeah? Okay, cool. Do we want to play around with this a bit? I mean, it depends. Do I want to go through all of the stuff in the architecture course, or do I want to deep dive into account sizes? I mean, there are the tests provided here. You can play around with this by yourself if you want. There's still so much to go through, and I'd rather just give you a higher level overview of all the program architecture stuff and not go too much into detail today. And we're already pretty long into this video, so let's keep moving and talk about dealing with accounts, at least a little bit, because we did talk about this already. So just one more time to reiterate, the data order is important. Order is important. That's also what they say in court. Order. The first consideration is fairly simple. As a rule of thumb, keep all the variable length fields at the end of the accounts. So that looks as follows. It's bad if you have a vector that is variable in length, where the first 4 bytes indicate the length, before all of your static things like your ID, like the constant length things. Because if I now want to find out the ID, then I first need to read how big is my vector, and then I can find out where my ID is stored. Whereas the other way around, if the ID was stored first, like this, and then all the variable stuff comes, then I know my ID is always at 0.0 or 8 with the offset for the discriminator. And the flags will then always be at 8 plus 8. So the 16th byte will be the first byte indicating the length of the vector for the flags. So having the variable length stuff behind the constant length stuff. Always good practice. This also then allows us to do searching for the ID on several accounts because it's always at the same point in the account. So I can always, at that offset of 8, search for a specific byte in all of my program accounts. And I couldn't do that if that ID is always somewhere else. Then I can't use this anymore. Then I need to write my own, more complicated searching. And that would then be really bad design. So having the constant length things first and the variable length things later is good design. And it's not just that. Like, I don't know how often you use that actual lookup really. It's also me as a program writing to those fields. Probably even more important. I actually don't agree with this. It's not the main problem, this lookup, because that lookup is client side. And on client, we have a bunch of resources for compute and whatever. It's a bit annoying, yes, but on-chain is what's important. So my on-chain lookup of the data, which is also lookup, but not what James describes here. On-chain, when I want to write to a specific part of the memory or read that specific part of the memory, I want to have the exact offset. That's also very important for this zero copy, right? Here we need to know where we want to write to. We need to have the index. And if that index is variable, then I first need to, find out where that index is. Whereas if all of my fields are constant in size, then I can work with indexes like this directly. When I always know the 32nd byte is always the one that I want to change or always the one that I want to read. Makes it a lot easier. So this is the on-chain kind of lookup for this account. Is it really a lookup? No, it's writing into that field. We can do that directly if we have the right order here. That's why here I think we can't have weird stuff like vectors. Let's try. A vector of U8s? No, there you go. This field does not implement the copy. I mean, the error might be a bit weird. But yeah, I think you just can't have stuff like this. You can't have variable stuff like this because you need to know exactly where to access this, because otherwise I can't do some really big data dot really big data, because the dot really big data, what that really does is it adds the offset of the, in this case, 8 bytes for the discriminator that comes before this and then allows for reading that data. So it knows where it needs to point to, because again, this whole thing here is just a pointer to the actual memory, and saying this pointer dot where in the memory do I need to point requires that I need to know how big all those things are, such that I can, if the next thing would be just an integer or U32, here I could then be like dot integer cannot transmute between types of different sizes. 128. Yeah, so this is more complicated than you might think. Yeah, but this works now. So it always has to have the same. Interesting. But yeah, point is, if I have this integer here, I need to know how big, or so how many integers come before. Here are 1024, such that if I were to write some big data dot integer, set it to, I don't know, whatever, I can do that because it knows where in the storage that is, because this has a fixed length. So this cannot be a vector. If it was a vector, then this wouldn't be a clear offset, but it would require reading some other data and then adjusting my index accordingly, which it doesn't do automatically. It doesn't allow that. So I can't have a string in here either. Yeah. Same thing, doesn't implement the copy, same as with vector. This stuff I can't do. Right, okay, so long story short, it's important for being able to access the correct location in the memory, and not just for this sort of a lookup, but also inside the program itself. Okay, I think that's enough for the data order. let's talk about future use. So we just mentioned that we want to have the fixed length things before and then the variable length things. But what if I have my fixed account structure like this, and then I decide, oh, now I need another number or whatever in my account that is fixed length. So I would like to add it here in between, but I can't because there comes the vector. And I could extend my accounts and make them bigger, reallocate them, and then put it at the end. But then I still have the problem that I can't quickly access it anymore as I could if it were before. So what we can do is we can add some padding like here for future use. This is just a bunch of data that we reserve in case we want to put something here later. So that later when we want to add our experience field or whatever, then we just change our struct to add this field so we can reference it and decrease the number of bytes that we reserved for future use by the amount that we require, and we put it in like this. And then we still have another 120 bytes for more field, and we could fill it up as we need later before we get to all the variable stuff. Doing it like this is great because it allows for backwards compatibility, because the event log will always start at the same location in V1 as well as V2 accounts. So we don't need to distinguish between which type of account is it. Is it still a V1 account? Because then it would be earlier. If it's a V2 account, then it would be later in the... So having it always at the same location is great. And in the V1 account, we just don't use those bytes for future use. And in the V2, there is this one byte that is just labeled differently. It's still the same in a way. It's still the same number of bytes, but now we can access it with .experience, the first byte in this array. Same as we did here, I added this integer. This is also just a label that I added. I mean, to make it really the same, I could do it like this, that my really big data is now one integer, one U128 less than it was before, and therefore I have this integer in the end. That is now the exact same account, just that I have a label for the last byte. So instead of doing this stuff, where I first need to find the index for the last byte, I could now just say really big data dot integer and then write my data there. So instead of this, I can now write this, just because I got the last byte out. I just labeled it differently. That's my point here. Same as here. I now label this differently, this one byte in my for future use. I label it differently, and that way allowing for it to actually be used. And I decide in this V2, I actually use those bytes now for this purpose. And the rest of the bytes I still hold as padding for potentially needing it later. And again, this is a trade-off. How much of this padding do you want to put in there? If it's too much, then you blow up your account and you essentially pay for space that you don't really need. But if it's not enough, then you run into the issue of you can't extend your accounts anymore, at least not neatly. So again, trade-off. Program architecture is a lot about trade-offs. As we said in the very beginning, knowing what possibilities there are, using this padding or not using this padding, what are the trade-offs between them, and then making an informed decision of what do I want to do and how big should my padding be, because possible implementations are I use this size padding, and another possible implementation is I use this size padding, and another this size, and another none at all, and another a huge one, many possibilities. So yeah, trade-offs. You don't want to make this too big, but you also don't want to make it too small. Unless you know that this account will always have this state and it's very unlikely that you'll add something, then don't use that, obviously. Or you only have fixed length things, then obviously you also don't need that, because you can, if you extend it, just put it there at the end, because you don't have any variable length, or you decided to make those variable length things fixed length, like the token metadata program does for names and symbols and the URI. They're actually strings, which would be variable in length, but they always put it with exact lengths. I think the URI was like 200 characters always, and the name like 32 or something like that. But yeah, they made it fixed such that they still have the quality of being able to access the remaining parts of their accounts with a fixed index. Those were design choices. They could have done it differently, but they chose to do it like that. They chose to go for this program architecture. So as a general rule of thumb, anytime you think that your account types have the potential to change in a way that will require some kind of complex migration, add some for future use bytes. It's not just the adding new stuff, it's also the maybe I want to throw something out and replace it with something else, but that might be bigger, etc, etc, etc. Cool, that's that. Next up, data optimization. What is this? Oh, I think we touched on that a little bit before. The idea here is to be aware of wasted bits or wasted bytes, really. We don't want to waste bytes. And if we have enough bits, then we can save on the actual bytes. Doesn't make any sense, and we'll continue. So for instance, if you have a field that represents the month of a year, you don't want to use a U64 because that gives you 2 to the power of 64 possibilities and you only ever need 12. So a U8 is much better. Still, a U8 gives you 256 options. And the cleanest way to do this is use an enum with labels. An enum will, as we learned, always just use 1 plus size of the smallest variant. And if the smallest variant is 0, because we don't have a variant, then it's just 1 still. Then it's just 1 byte. So the clean way is to use an enum, but it's also 1 byte. Like we don't save anything if we just store it as a U8 or as an enum. It's just nicer to work with if it's an enum. If we want to get more aggressive on saving bits, we can group together booleans. Like we already discussed before, because each boolean needs 1 byte, we can aggregate them into actual bytes and use the individual bits of a byte for the individual booleans. So we don't use the Borscht deserialization anymore, and we'll then have to manually decode that and just work with bits. And that stuff is really funny. Like if you're new to programming, I challenge you to try out stuff like this. Make yourself one U8 that represents 8 different booleans and see how can you quickly get to a value that you want. How can you quickly access one of those flags from the total accumulated status flags, and how do you need to store them if you want to have 8 separate ones? How do you need to logically combine them? I love working with bit shift operators and binary arithmetic, that's hard to say, and binary arithmetic to work with those things. Yes, it's not as easy, and that's the next trade-off here, could lead to bugs because, you know, the more complex it is, the more likely there is to be a bug in there because you might make a mistake. So for security purposes, especially if you're unsure, it would be nicer to store the flags as individual booleans like so, because there you definitely can't get it wrong. Well, it's way more difficult to get it wrong. You can still have a typo and write blessed instead of burning. But if you know what you're doing, this is a nice way to save 7 bytes if you have 8 booleans. Trade-off, of course, is now you have to do bitwise operations. But that's worth having in your toolkit. Yeah, I agree. Cool. Indexing. I'm gonna speed through this now because there's still a lot coming up. Holy sh. This last account concept is fun. Yes. And illustrates the power of PDAs. Ooh, we're gonna work with PDAs. Nice. When creating program accounts, you can specify the seed used to derive the PDA. Okay, so far so good. Yes. This is exceptionally powerful since it lets you derive the account addresses rather than store them. Yes, I think I made an entire video just about that. Yeah, dictionary, I think that was it. Mapping data using PDAs. If you want to see that, go there. So the best example is the good old associated token accounts. This is how most of the SPL tokens are stored. Rather than keeping a database of the SPL token account addresses, we only have to know the wallet address and the mint address, and then we can derive the ATA. So that's actually quite nice. Indirectly, we know this, but let's explicitly go over this again because I use it all the time and it makes sense to understand this. We can have different relationships here. For instance, if we just need one account per program, a global account, then we just need some static seeds like lookup, that is one per program, here, one per program, and then you set, then it's always this account. Because remember, PDAs take the seeds plus the program ID. And since your program ID is fixed with the same seed, you will always get the same PDA then. So we just use a static, I like to call it static, one static seed to create a global account. And that is then the same account for our program, for all the instructions. Something like my program's treasury. If my program has one treasury, then I do something like this, seed, treasury, and we're good. Then we can have one per owner, one per user. So if every user needs an account, then I'll use some static thing in the beginning plus the owner key. So this static thing in the beginning I do such that it's clear what type of account that is. I could theoretically leave it out if my program only has one type of account, and good practice, even in that case, is to use some static thing here before, for reasons that we have discussed in one of the security videos, this one, securing your PDA seeds, which you can also find here. So yeah, something static, and then the user's public key, such that with the same user, you'll get the same account. Pretty simple. And you don't need to remember the account for the user, so you don't need to build an index where, oh, this user has this account. No, we can just use a PDA where we use the user's public key as part of the seeds, and then it's always the same PDA, and so we always know which account that is. That's a really nice feature of Solana that you just want to use because it makes stuff so much easier than letting the user choose their own account by creating a new key pair and putting that in, and then you need to remember. That's no good. Use a PDA. Makes it so much simpler. Plus, it also ensures that I can always be just one of those accounts. The user can't create two. Cool, multiple per owner. Now, what if we want to have multiple? Well, we just need to add something more. Some episode number to bytes or whatever this could be. Could also be a string, like the title of whatever, right? But there it gets meh. But this stuff allows you to do something like have exactly 50 or maximum 50 per user. You just go episode number up to 50 and then you don't allow more. But what's way more often the case than this is a one per owner per account. So it depends on some user and some other account. So the combination of this user and this account. So for this account, for this user, we create a new account. For instance, something like a game instance. And in each game, every user can have an account, like a player. For the game, for the user, we create one player. And in the same game, a different user has a different player. And in a different game, the same user also has a different player. But as soon as we're in the same game with the same user, we have the same account. And that's the one per owner per account. How do we do that? Well, obviously, again, after some static stuff, we use both the user and the other account for the seeds, as we do in the ATA, where we use the owner and the mint. For each owner, for each token, there is one associated token account. And really the ATAs are a per owner per account kind of a thing. For each user, for each mint, for each token program, there's exactly one account, because they're different token programs as well. And all of that can be done with PDAs. And we never need to remember where the account is because it's always deterministically derived based on the user and the other accounts and whatnot. And here's an example how you would do that. So every user gets a channel account, and then they can create arbitrarily many podcasts accounts. First, they create one channel. So there's one channel per user. We see that here. And then they can create as many podcasts as they want because they just take the episode number, and the episode number goes from 012 to X. That X I would take from the episodes created. So if I create a new one, then I increase the episodes created and therefore know what the next X is, so I can put the right index here. So it's still deterministic. I know how many accounts there are, unless I allow for podcast deletion as well. That's one clean way how to index all the podcasts for one user. And then I can quickly derive all of the podcast accounts for a user because I know how many he created, and then I just derive all of those PDAs. Pretty simple. Cool, done. Last topic for today, dealing with concurrency. Without reading this, let me scroll up and explain it to you. If we have such an account where it just depends on the owner, we're pretty much fine. The owner can access his channel and his podcasts, it's fine. Unless somebody else can write to that, which would be weird. However, with those one per program accounts, it can get more problematic because remember on Solana, we need to specify if we want to write to an account. And if we specified that, then this basically stops several transactions with that writable account to be executed in parallel. So if there are several transactions that want to write to the same account, they can't be executed in parallel, but they need to be sequentially. Yes, everything is really sequentially because it's a blockchain and it's a clear this transaction comes before this one, etc. But for the calculation of that, the runtime works in parallel because where the state is not influenced, we don't care. We can calculate it in parallel and then pretend that it was executed sequentially because there's no overlap in the state. However, if there is overlap in the state because we want to write to the same account, then we can't do that. And that could result in the performance of your program going down because there are just too many requests for the same state. This really only becomes relevant if there are really a lot of requests on your program. Again, on Solana, we can have quite some TPS. But if there are like a bunch of requests, let's think of something like the token program. If the token program had one global account that is writable and that requires to be writable and requires to be called in every transfer, that could be problematic, highly problematic, because suddenly we can't parallelize all of the token transfers anymore. And then you can imagine how bad that would be, right? And the token program is probably a bad example because that's really popular, but even something like, I don't know, an exchange, a DEX or something. If there are a lot of requests, you want them to use as little common state, writable common state as possible. If you just read, it's fine if they all read from the same. The system program is also just readable and can be in every instruction. That's fine, as long as it's just readable. But with writable, that's where the problem comes in. So anyway, what does James write here? Because I'm explaining what I think this is about, and I'm not sure if it's actually about that. Okay, so James starts out with an example for a candy machine, because the candy machine needs to be writable. There's one big account that holds all the data for that one mint, and that's the state that everybody is competing for in such an NFT mint. Simple example, Alice wants to pay Carol and Bob wants to pay Dean. That works in parallel because they don't influence each other. But now, if Bob also wants to pay Carol, then we can't do that in parallel anymore, because obviously one of them needs to go first. And the next one depends on the state change of the Carol account, because otherwise we would delete money. So that doesn't work. Fortunately, Solana is wicked fast. So it'll probably seem like they get paid at the same time. But what if there are a bunch of people trying to pay the same? So if there are 1,000 people, each of the 1,000 instructions are queued to run in sequence. And some of them will get queued. Average case, you'll just need to wait longer. And worst case, the transaction will fail because eventually the block hash will expire before it manages to get in there. Or it would have to be forwarded to too many validators and they just then can't be bothered to forward it anymore. And this paying Carol might be a bit of an arbitrary example because there are not going to be 1,000 people at the same time wanting to pay Carol. Unless Carol was your program and you have one treasury where you accumulate all the funds, then suddenly that's exactly what you're doing. Every user has to pay your account, so that account needs to be writable. So if we have this one treasury account that everybody is using, then we get exactly there. So what's the solution? Separate the data transaction from the fee transaction. For example, we have an account donation tally. Its only function is to record how much you have donated to a specific hard-coded community wallet. Let's look at the suboptimal solution, where we transfer from the owner account to the community wallet and we track how many we donated. Now let's look at the optimized solution. Still do the same checks. Then we do a transfer from the owner to the donation tally account. So we transfer to that account such that we don't need the community wallet as writable. We do the transfer and we add those lamperts to donate to a redeem field, and then in a separate instruction, and this could now be permissionless, anybody could theoretically do that, or you run the crank yourself. You transfer from that donation tally account, and remember how here we don't need the system program anymore. We don't need to have a CPI context because those are both accounts that we own. Okay, the community wallet doesn't actually need to be, but the donation wallet, so the donation tally, that's an account that we own. Like the program owns this. The program is the owner of this account. Again, I made a video about all of that stuff up there. That's why we can just dereference the mutable lamperts and subtract from there directly. So we directly write into the lamperts field, subtract and add to the community wallet. That's that. So we split just the one donation, so that transfer out of the user's wallet into a temporary account or their donation account, and then we accrue them into the one wallet that holds all the funds at some later point in some other transaction, such that for this thing there is no bottleneck. Yes, it's a bit annoying because we have two transactions that we need to run, but therefore we don't have a bottleneck here. Basically, we just moved the bottleneck to somewhere else, and that somewhere else is less important. Or we can say that we might not have that many users, but each user might have a lot of requests, like a lot of individual donations. Then this is actually more efficient because we always add to this value and then only once move all the funds to that community wallet. So we can get out the fees maybe once a week or something, whatever, because it doesn't really matter. We can keep it in there for a bit until we get it out into our community wallet. And this stuff we could do with clockwork, but that's a topic for another video. Ultimately, this is a design decision. You need to estimate how much traffic you'll actually have, and if that bottleneck will actually be such a small bottleneck that it actually limits you, or is the bottleneck big enough anyway that everything works just fine? Then I don't need to separate that. If I would write a program that only one person uses every day, I don't need to do that. But if there are like millions that want to write to the same account, then maybe yes, I want to do something like that. You can always run a simulation to see your worst, best, and median cases. Yeah, so just try it out, essentially. Or start with that and then realize, oh, some stuff is not working. I know why it's not working because I have that bottleneck, and then change to this. Easy. Okay, we've already looked at this. That's basically that source code here. There is examples for all of that. There we have this with the bottleneck, and there we have it too without the bottleneck. So basically what we saw here, that's all in this GitHub that I also encourage you to check out and play around with. Coming to the conclusion of today's video, we've talked about quite a few program architecture considerations. Bytes, accounts, bottlenecks, and more. Words. James does the same way. Hopefully the examples and discussions sparked some thought. I always say, hopefully it was helpful. At the end of the day, and this is important again, I agree with this. At the end of the day, you're the designer of your system. It's your job to weigh the pros and cons of the various solutions. Be forward thinking, be practical. And there is no one good way. As I said, it's always trade-offs. You can't do it perfectly. If you choose one thing, then you might lack another thing, and you just need to find a good solution for your program. Just be aware of the trade-offs and architect your program to the best of your ability. Cool! There's still this demo that you can go through, and I mean, it's really nicely documented. I would recommend that you try it out yourself, such that you get some practice, or also just read through that part and then attempt the challenge that is at the very end, or just go through your own programs that you've developed so far or that you're currently working on and see what you can do in terms of memory management, storage size, and concurrency. If there are any issues that could arise, or if you would build it again, what would you make better next time? How could you better lay out the PDAs? Or how could you be more efficient with storage? Just some things to think about. I will end it here because it's been a long video, huh? Yeah, hope it was helpful. Hope you learned something about program architecture. I would say this is done. And I might come back next time talking about oracles and oracle networks. Let me know in the comments if that is something that you would be interested in, or you want to know more about verifiable randomness, or if we should talk about CNFTs again. If you enjoyed this, if you found it helpful, like this video. If you haven't already, please subscribe, and you can watch those videos. Or here you will find the entire playlist of this Solana development course. I've made a bunch of videos on that already. So yeah, see you around. Till next time. Thank you for watching.